My name is Adam Brady, and I'm going to discuss the work of my co-authors and I on influent geochemistry and hydraulic resonance influences on microbial respiration and trace organic attenuation within saturated woodchip bioreactors. Woodchip bioreactors are created using lignocellulose substrates as geomedia and have been proven in treating agricultural runoff, mining impaired waters, and stormwater. They're a passive treatment system that can be used outside of areas with centralized infrastructure services. There has been limited investigation focused on the impact of residence time on redox conditions within saturated woodchip bioreactors. Additionally, there's been limited investigation on impact of redox conditions on trace organic removal outside of wastewater treatment plants or riverbank filtration. We hypothesized that the redox conditions within the system, manipulated through nitrate concentration and hydraulic resonance time, would create environments more conducive to the removal of specific trace organic compounds, providing an opportunity to understand the potential for saturated woodchip bioreactors as a standalone technology. To assess the potential of a saturated woodchip bioreactor to remove trace organic compounds under nitrate and sulfate reducing conditions, a system of 8 upflow columns and 4 different redox conditions were evaluated. The trace organics used are commonly found in wastewater treatment plant effluent and the waters receiving it. The columns were packed with 12 grams of substrate and were operated for 54 days. The substrate included alfalfa hay and ground pine chips. To support temporal sampling, 3 mesh bags containing 1 gram of substrate with the same ratio and substrate as the columns were placed side by side in the column top. Each column received 100 milligrams per liter sulfate and a varying nitrate concentration as nitrogen. The concentration varied from 0 milligrams per liter as nitrogen to 10, 20, and 40. What you're seeing here are effluent geochemistry across all 4 sets of duplicate columns and at both HRTs. Of note, you'll see a dashed red line where the HRT was transitioned from 12 hours to 24 hours in each panel. The 0 milligrams per liter columns received no nitrogen, as seen in panel A, while effluent aqueous sulfide concentrations increased as the HRT increased. The 10 milligrams per liter columns completed nitrate reduction somewhere in the columns at both HRTs, as seen here in panel B. However, the columns only transitioned to sulfate reduction at the longer HRT. The effluent nitrogen species in the 20 milligrams per liter column, seen in panel C, and the 40 milligrams per liter columns, seen in panel D, provide evidence for nitrate-reducing conditions predominantly occurring within the system through both HRTs, though the percent removed increased as the HRT increased. Neither set of columns exhibited sulfate reduction at any point during the experiment. Microbial samples were binned based on the presence of effluent aqueous sulfide. In panel A, the phylogenetic distances between the redox conditions suggest an impact on microbial ecology due to those redox conditions within the columns show a significant difference between 0 to 10 milligrams per liter in blue and the 20 to 40 milligram per liter samples in red. The observed number of ASVs in the sulfate reducing columns, once again 0 to 10 milligrams per liter seen here in blue, is significantly different from the 20 to 40 milligrams per liter or the nitrate reducing columns seen here in red, supporting the assertion. Panel C shows the nitrate gradient within the columns created a very compelling gradient for the nitrite reductase NIR-S, which is used as a proxy for nitrate reduction within each column type, providing another piece of evidence suggesting varying redox conditions within the columns. Here we're comparing trace organic attenuation for the 3 compounds that were attenuated, as well as a representative recalcitrant compound. Atenolol in panel A underwent the largest transformation in the nitrate reducing conditions found in 20 milligrams per liter, seen here in the dark green, and 40 milligrams per liter, seen in the yellow. Trimethoprim, which can be seen in panel B, demonstrated the largest removal in sulfate-reducing conditions, seen here in blue, in the 0 milligrams per liter column, which is blue, and in the 10 milligrams per liter column only during the longer HRT, seen here in green. Sulfamethoxazole, down in panel C, demonstrated similar removal across all redox conditions, increasing only as HRT was increased. And panel D shows carbamazepine, which is used as a recalcitrant compound that demonstrates limited removal in any redox condition or HRT. Extending the HRT impacted the redox conditions within the constraints created by the influent geochemistry. In the 0, 20, and 40 milligrams per liter nitrate columns, the prevalent redox condition was exacerbated. In the 10 milligram per liter column, the redox conditions transitioned from predominantly nitrate reducing to sulfate reducing only when the HRT was expanded. As we will see with TrOCs removal, the shift in redox conditions resulted in increased removal of some trace organics. Atenolol has been previously shown to be susceptible to biotransformation in open water wetlands and stream biofilms. The data in our investigation suggests that biotransformation of atenolol would be highest with increased nitrate-reducing conditions created by increased nitrate concentrations and an increased HRT. This finding indicates that compounds may transform which undergo rapid biotransformation under oxic conditions may transform more slowly when sulfate reduction is predominant, such that the removal of these compounds should be targeted in systems that are also designed to treat nitrate. This investigation suggested that trimethoprim may be more susceptible to enzymes and metabolic processes happening under sulfate-reducing conditions compared to nitrate-reducing conditions. Given that trimethoprim removal increased as sulfate-reducing conditions increased, the data suggests that saturated woodchip bioreactors could be used to augment a passive treatment system, making the overall system more efficient with respect to trimethoprim removal. Our investigation suggests that HRT can be used as a design parameter within woodchip bioreactors to impact the overall removal of sulfamethoxazole without regard to the nitrate or sulfate reducing conditions found within the system. Given that the removal of sulfamethoxazole is still less than 25% within the conditions of the experiment, other removal methods may be needed based on the priority of sulfamethoxazole removal within a treatment train. As we demonstrated showing carbamazepine, there were 3 compounds that were not removed appreciably during the experiment. Carbamazepine is known to be very recalcitrant, and future research is needed to determine if there are geochemical conditions or a corresponding HRT within a saturated woodchip bioreactor that may support its removal. Emtricitabine, the lack of removal is similar to other studies that have shown emtricitabine is biotransformed slowly, suggesting that our HRTs may not have been long enough for removal to be seen. And the lack of removal of metoprolol suggests that other unit processes must be added to woodchip bioreactors if metoprolol is of concern within a source water. So in conclusion, we determined that in allowing diverse redox conditions to occur by design based on source water composition, a saturated woodchip bioreactor may increase the removal effectiveness of certain trace organic compounds. The manipulation of HRT demonstrates the opportunity to use residence time as a design factor for desired performance objectives, and saturated woodchip bioreactors demonstrate the potential to be used as a standalone technology or as a unit process inside a larger treatment train. This investigation was in collaboration with Michael Vega, Angela Stiegler, Dr. Rachel Scholes, and Dr. David Seflak at UC Berkeley, and mine's undergraduate research assistants Kim Riddle and Henry Peel, along with Dr. Josh Sharp. This work was supported by the NSF-funded ERC for Reinventing the Nation's Urban Water Infrastructure, or Renew It, a grant from the Colorado Higher Education Competitive Research Authority, CHECRA, and the National Institutes of Water Research. Additional support was provided by the U.S. Army's Advanced Civil Schooling Program and the Department of Geography and Environmental Engineering at the United States Military Academy. Thank you for your time, and I look forward to your questions.